What happened on June 23rd, 2020? You know what happened? I know one of my friends got married. What happened in your life on June 23rd, 2020? Nothing? It was like COVID stuff, right? Beginning of COVID, right? Everybody was panicking and shutting down and everybody stay home and stuff, right? It was crazy time. But I got an interesting email from the then president of the University of Utah, or former president, Professor Dave Pershing, who's a faculty in our department. That tells you a lot about our department. So he sent us an email. Look at the top. Hi, guys. See the note from Pat Richards below. Who is Pat Richards? Former director of the Utah Symphony and Utah Opera. I'm like, oh, what does the Utah Symphony and Utah Opera want from us? So it looks like she was looking to do some CFD modeling, some modeling of aerosols from wind instruments. Those wind instruments, if one of them is sick, there's no vaccine, everybody was scared of this virus. Like you bring a flute player or a trumpet player and they're sick, they cannot mask the trumpet, right? It's going to mess up with the sound. The piano player can put a mask, 5 masks if they want, right? The string instruments, they can put masks. But what do you do with the wind instruments? Trombone, trumpet, flute, bassoon, oboe. What do you do with those? They're respiratory droplet factories. Does anyone play a wind instrument here? All right, so you can tell the reeds are usually pretty wet. There's a lot of respiratory droplet emissions coming out. So, you know, for all they know, they could kill everyone in the orchestra. And they wanted to understand that. Now, at the time, I'll give you some statistics. There are 316 national orchestras in the United States. So those are the big symphonies. And all of them were shut down for the season. No music. People were already kind of depressed with being shut down and staying home. They can't listen to live music anymore. Everybody was shut down. But the Utah Symphony wanted to see if they can actually resume playing and bring some hope, you know, to the population. So they reached out to us and like, my work is in computational fluid dynamics. That's what CFD stands for. It's a method, it's a research area where we study how air flows using computers. Okay? So I can take this room, for example, and look at these vents up here and over in the back and analyze on a computer how the air comes in and moves over there, cools you off. Most of the time it works. In many buildings it doesn't work on this campus. But that's okay, we can study that. But can we study how the virus moves? Like, I don't know. But then, you know, we were sitting home. You know, I was we just had a new baby, you know, and between the crying and waking up at night, it hit me that we can actually do this, and we can do it very, very effectively. So I'll explain to you what we did. This is a picture of the Abravanel Hall. If you're from Utah and Salt Lake, you've probably visited there. If you haven't, you should. If you're new to Utah and Salt Lake, you definitely should go and check out Abravanel Hall. It's in downtown. Go listen to the Utah Symphony. You can go in when they're practicing. Also, I think it's free when they're practicing. But they wanted to study, and they were concerned about the wind instrument emissions from possible COVID-19 infections, and they wanted to study, you know, what happens, or if we can even have a chance at resuming performances. This is what's called a Schlieren technique. It's a way to visualize heat and, like, you know, the mirage effect you see in the high desert. You're like climbing up the road. It's so hot. You see this you think it's like a pond or something. It's just the change in density because the hot air, the heat from the ground makes the air hotter, and the hotter air is going to rise up. So that's what you see in the mirage effect. But you can also see stuff coming out from the tip of the instrument. So this is just heat, but with that, there's also a lot of respiratory droplets coming out from these instruments. Okay. So here's the crazy idea we had. We said, okay, a virus is a tiny little speck of RNA or something molecular. I don't understand it. It's just very small, I know. But the only way for it to be transmitted from one person to another is for it, at least as we know, is for it to be attached, at least respiratory diseases, for them to be attached to respiratory droplets. So think of these blue bubbles here as your respiratory droplets, and these green specks of goo over there, magnified to like 1,000%, they're the viruses attached to these droplets. Okay? And that's my wireless mechanism. That's a person's wireless mechanism to infect you at a distance. They will sneeze, they will say hello, and those respiratory droplets travel carrying the virus. You inhale them, and you get infected. So we came up with this idea that we said, if we can track the airflow, we can track where the viruses go. Why? Because the respiratory droplets are moving with the air. They're called aerosols. Aerosols means droplets that can be transported by the air. Right? Aeroplane. It's a device that flies in the air. Aerosol, it's a particle that flies in the air, right? There are bigger droplets that deposit on surfaces. We can wipe those off very quickly with whatever solution or formula we have to sanitize them. Okay, so we went down to Abravanel Hall. It's a huge venue, magnificent. The smell of the wood in there, it's just like gives you the shivers. I had a mask on, I took it off because I just wanted to smell the wood, but then, when everybody was looking, I had to put the mask back on. But this is our team here. This was one of my students, Hayden. This is a 32-foot long beam. Nobody dared go up except him. I think he does like parachute diving or something. So he was like, yeah, I'll do it. Like, do you need to sign your waiver? No. So he went up there. He was happy to take measurement of what? Well, there's inlet vents up there. You see all of those black lines between the lights? Those are the inlet vents to cool off this huge venue. It's a magnificent venue. Okay, those are the inlet vents. Now, there's a door here. We call that stage left and call that stage right. If there's a classical music connoisseur here, please correct me if I'm wrong. I had to learn those terms when I went there. This is, I think, the stage. You're standing on the stage facing the audience. This would be stage left, and this would be stage right. And then they had some return vents in the back. Why do we need this information? Again, remember our hypothesis. If we track the airflow, we can determine where the viruses go. To track the airflow, I need to know where the air is coming in and where it's leaving, right? So it's going to come in from the top, good, and then it's going to leave through the return vents. So we needed to measure those. This was our team, again. So that's me with the Utah mask, and I had like this big shield in front of me. And Hayden in the back, right here. And this is one of my other students, Mokbel, one of our other students, Josh. We were taking measurements and these devices in our hands, anemometers and thermocouples, a bunch of things to measure the air velocity and temperature and all of that. Okay. So then we asked for the orchestra to give us their seating arrangement. We understand the airflow. That's one piece of the puzzle. But the next item of business is to figure out where the particles are coming from, the aerosols are coming from. So they gave us the seating arrangement. And then we went ahead and redid it in a way that can emphasize the importance of the emissions. So you see up here the violins, they're all in gray because they're going to be masked, the cellos, etc. The piano over here, harp, and the Glock, and the bass drum, timpani in the back, percussions. All the other colored circles are wind instruments: trumpet, French horn, clarinet, oboe, flute, bassoon, and tuba. Okay. Now there are two dimensions on that plot. There's the size of the circle and the color of the circle. The size of the circle tells you how many aerosol particles the instrument is emitting per second. So the larger the circle, the more particles it's spewing out per second. So you see the trumpet, for example, it's about 1,100 particles per second. The trombone comes next, 235, then the clarinet, and you see the size shrink, all the way down to the flute, which was the smallest, about 8 particles per second, 8 aerosol particles per second, okay? 8 aerosols per second. The color determines the speed of those aerosols. Are they just going to come out and fall down on the floor? Or they're just going to shoot out and then be carried with the air? Red is fastest and blue is slowest. So now the worst combination is going to be red and big circle, which is going to be the trumpet. So the trumpet not only emits a large number of particles, it can potentially send them flying across the stage, right? Look at the flute, on the other hand. Very little number of particles. It's at the bottom, but the flute has a strong jet coming out. So although it's emitting only 8 particles per second, it can shoot them across. So you'll see in our results later that the flute, all of the particles from the flute are flooding the violinists over here. Okay? Then you see the French horn, for example, it's kind of average size in terms of how many particles it emits, but also average speed for the jet that's coming out. The tuba is little number of particles and very slow. So it's just like, just kind of coming out and just falling down, okay? They eventually get transported by the air because they're aerosols. They have to be transported by the air. Okay, so we thought of this. We did this diagram. We were so excited that we created this. But then what? We haven't done anything yet. So how do we do this? We said that we know the equations that govern airflow. They're called the Navier-Stokes equations. You will learn them next year when you take fluids. They're very complicated nonlinear partial differential equations. You see them here. There's 4 of them, one in each direction, and then one equation to conserve mass. And then we also want to add an equation to track the aerosols. I want to track the aerosol coming from the flute, the aerosols coming from the trumpet, the aerosols coming from the oboe. But soon there's like about 8 more equations we need to solve. A lot of these equations, and we need to solve them in 3 dimensions, okay? Did you have a question? Oh, yeah. Then we used numerical methods, which I suppose is the course you're here for. We use numerical methods to solve these equations, and that's really the only way we can solve them. Some people say now they're using AI and data science. We'll talk about that at the end of the semester. But let me show you our results. So this is the hall. This is at least our back of the envelope representation of the hall, because we had like 2 weeks. They told us we have 2 weeks to figure this out. Otherwise, they're going to be shut down for the season. These cylinders here are the players, okay? We just approximated them as cylinders, you know, just to place them at a point. We had the piano over here, the glog, the timpani, and what you're looking at, if you see those red spots at the top, those are the inlet vents. So we're going to expect to see the air coming down from the top, and it's going to come in and mix and move around. Now, what I'm showing here are only a few slices. So this is a 3-dimensional flow. It's impossible to visualize in 3 dimensions. So you can only visualize like in 2D. And so I'm taking slices across, and I'm going to show the speed of the air, but sped up. So the speed of the air, but I'm speeding up this, the animation so that we can see it. In real time, these are very slow-moving currents, okay? Let's see what happens. So the air comes in at high speed. It comes down, kind of hits the bottom, and starts recirculating and mixing. And this is happening in 3D. In the middle, you know, you see kind of less of that mixing, but you still kind of identify there's like these 2 big, there's a front recirculation and a back recirculation, okay? Now, another way to visualize this is what we call streamlines, and we track the particles, how the airflow particles, not the aerosol particles, just the airflow, how the air is moving. And you can see that there's like this big region over here that's kind of spinning around. These look like spaghetti or noodles, right? And in the back, you see another region. It's like a dead zone in the middle. Okay, so that tells you kind of about the air in that, the air flow in Abravanel hole. Next, we're going to look at the particles. Now, this is the original arrangement. Up here, there's the violinists and then the cellos. But then here you see the flute. Now, the flute and all the wind instruments, you see this red spot at them. This is what we're doing here is saying each of these instruments is spitting out aerosols. So and that's going to be designated by this red color, okay? Now, you see the flute, there's two spots on them because there's the flautist at the tip by the reed. There's an opening over there that also emits particles, and there's the end of the flute. So you see two spots here. And what you're going to look at here are the concentration of aerosols, particles per liter. So 1 liter of air, 1 cubic meter of air, okay? And yellow is going to be 0.1 particle per liter. There's no 0.1 particle per liter. What that means that in every 10 liters, there's 1 particle, 1 aerosol, okay? Orange is going to be 1 particle per liter. Red is going to be 10 particles per liter, okay? And anything above red anything red is going to be 10 or more, essentially. Okay, so let's see what happens. So now the air is coming, and the players are emitting constantly. They're playing their instruments nonstop. And you see this whole mess of like particles, aerosol particles everywhere. Now, obviously, this is the worst case scenario because the trumpet might play for 10 seconds, then the oboe might play for 30 seconds, then the clarinet might play. They're not all going to play necessarily together. But if we can fix the worst case scenario, then the best case scenario is going to be better. Okay, so that was our assumption. But then we realized, like, this is bad. This is not good. Okay, this is not good. Then we thought, okay, how about we open the doors? And historically, the way we were thinking about it, I imagined like riding an Uber, and the driver is smoking. Okay, you don't see that in the US, but like I was out of the country, and the driver was smoking. Like, what am I going to do? I open the windows, right? You open the windows, you tell the driver, please open the windows, blast the AC on, so, you know, get that air out, get the smoke out. So we thought, okay, let's open the doors and see what happens. So we went ahead, remember the stage left and stage right doors, those two doors, we opened them. Now, that building over there, luckily, had high pressure inside it compared to outside. So you open this door, it's like this beautiful breeze. It's like you're in a tropical beach. Seriously, it was so windy because it was highly compressed. The building was compressed compared to the outside. So the air was leaving. And we thought this is great because these two openings are going to give us more vents to clear out the aerosols. We ran the calculation. We ran the calculation. And again, we noticed that the doors only affected the instruments close to them. They didn't have much reach into the inside, okay? And when we analyzed this with these colored streamlines, you see the purple noodles over here, they just show us the extent of the effect of the doors. It only reaches a few meters into the hole, not to the inside. It's not going to be good. If we want to clear those aerosols, we need a better solution. Now remember, all of this is done with numerical methods applied on these equations. And each of those calculations would take us a couple of days. We would visualize it, run it. In this course, you're going to learn techniques that will set you up for doing something like this. Okay. So now this resulted in a science paper. So this is real stuff, real engineering stuff, to demonstrate to you a little bit that what you're learning here is not something just an academic exercise. Okay, so we noticed that we have vents over here, return vents, and we also have return vents in the back, okay? Kind of looks like an angry, eyes with two eyebrows, but that's kind of what it looks like. And if we need to make an improvement on getting these aerosols out, we need to make sure that the super emitters and the super spreaders, whatever they categorize them. So essentially, the trumpet and the flute, all of those, they're seated close to what? Return vents, or vents that take all of these aerosols out of the building. And then we proposed the unthinkable. Guess what? We told them we want to rearrange the orchestra. What? If you know classical music, I mean, an orchestral arrangement is an art. It took centuries to come up with orchestral arrangements. And for each orchestra, for each hall, they do acoustic studies just to be able to place the instruments within centimeters of each other to make sure the acoustics are perfect. So we told them, hey, to fix this, we need to rearrange the orchestra. And then Thierry Fischer, at the time he was the conductor, he said, do whatever you need to do to keep everybody safe. I want to open the Utah Symphony. We're like, okay, let's do it. So we took our original arrangement and we overlaid that calculation where it showed us where we have the extent of return vents, okay? So I'm going to move all the non-wind instruments out of the way. And we decided we had now Hayden was a classical musician. He knew a lot about orchestra. I think he's going to be a conductor one day. So he was of tremendous help for us. So we proposed we put the trumpets and the trombone in the back, closest to the vents. Why? These guys have big circles and reds. They emit strong jets and a lot of particles. So let's put them right above those return vents. Then we put the clarinets in the back, flutes over here, French horn, oboe, tuba, bassoons. We rearranged them. Look what we did. We're trying to place everyone within those regions where we have these return vents. This was not the only arrangement we could come up with, but it was the one that gave us the quickest solution, at least that was satisfactory. Then we brought back the percussions, and we came up with an entirely new orchestral arrangement, just based on math and science, okay? That's incredible. Now see what happened. All the aerosols have a way to get the heck out of the stage. Okay, this was incredible. We were so thrilled at this finding. Then what we did clearly a very quantitative study. So we said what we care about is the breathing zone. If someone is within, chest level to a little bit above, head level, these instrumentalists are sitting. Some of them are very tall. So we took an average between like 80 centimeters to about 2 meters. We averaged all the aerosol concentrations to see kind of what the orchestra would look like. This is what the distribution looks like in the original arrangement. Like I told you, the flutes, they were flooding the violins in front of them. Although they emit little particles, but they have a strong jet coming out, okay? And this was the original arrangement. This is the new arrangement. On average, we reduced the particle concentration by a factor of 100. And believe it or not, they took our advice. They were the first symphony to open up its doors during COVID. And after that, other symphonies started reaching out to us to do similar analyses for them. It was the best work of my life. We ended up on KUER. You can hear the interview. There's both it's like a news article and an interview with Caroline Ballard and a New York Times article, a bunch of other things. You can find them on my YouTube channel. But this is what numerical methods can do for you. Okay, this is what numerical methods can do for you. This is the age of computing and data. Okay, using math and programming and computers and numerical methods and data to do stuff like this. Okay, all right. Well, let's begin. Welcome to Numerical Methods. I hope you're on the right course. If you're not, I hope you enjoyed the discussion. But my guess is that you're all in the right place. Okay. Let me see. I cannot figure out the lighting very well here. I don't want it to be too dim lest you fall asleep, but I also want to make sure that these are bright enough for you. So Chemical Engineering 2450, Numerical Methods. I kind of want you to hate and be afraid of this course. I want you to hate it and be afraid of it. I want it to stress you out because it is going to be the most important course in your career. Believe it or not, yes, it's my course, and I think it's the most important. Every professor thinks their course is the most important. But really, this is the most important courses you will take because it gives you tools to succeed. It gives you the way, the procedure, and how to think about problems as you tackle your future courses. It will make your life incredibly easy in the rest of your education and career. So be stressed a little bit about it so that you take it seriously, please. Okay? It has a very tough reputation. Okay, and I always have emails before, I always get emails before the semester starts, like, hey, Professor Saad, we hear the course is very difficult. What resources can we use? I'm like, yeah, it is a difficult course, and you better take it seriously. But, you know, we will work together on, I mean, you're here to learn, right? So we'll work together to get you through the finish line, okay? Today's objectives are to just get to know you and for you to know me a little bit. We'll go over the syllabus, some administrative stuff, some of the rules, perspective and importance of numerical methods. If this doesn't make the case for you, we'll present some other perspectives as well. We'll talk about programming in Python and my teaching philosophy. First and foremost, my name is Tony Saad, so you can pronounce that Saad or Saad. Technically, it's Saad, and you can call me Dr. Saad or Professor Saad. I will not respond to messages or emails saying, hey, Tony, or yo, Tony, or hi, Tony. I will not respond to that. I know some professors go by first name. I go by my title, okay? And the next order of business is for me to know your names. It's easier for you to remember one more name, right? But for me, I'd like to at least remember most of your names. So I would like to ask you to grab a piece of paper and write your name on it, fold it, put it in front of you. Use a nice size font so I can see, okay? And I will try to start remembering your names. If you have a Sharpie, that's even better. Don't use Word Art or whatever Microsoft Word does. Just make it something that I can read from a distance, please. It's like every time I ask this question, I recognize that my vision is getting worse year after year. Thank you, Gian. I can see it from here. All right. Okay. While you do that, we'll get moving. We'll start with syllabus and administration. I want you to meet your TAs. We have one of them here, Davin in the back. He's going to be one of your TAs. Lillian Prescott will be here on Thursday, and you'll get to know her. You need to know your TAs very well. You're going to be working with them and me, but you're going to be working with them a lot because they run the help sessions, and they are responsible for grading your homework assignments and giving you feedback. So get to know them. They're going to be your go-to people. If you have anything to discuss about the course, we'll discuss the rules of how we communicate with each other as we go through. But we got Davin in the back. Remember him. He will be running 2 of the help sessions. We have 4 help sessions each week. I'll discuss that on the next slide. And he'll be running 2 of them. So starting with the administrative stuff, it's such a small font. I apologize, but I had to pack so much into this slide. So the only official sanctioned resources for this course are Canvas and my YouTube channel. Canvas is where I will post your homework assignments, where you will upload your homework assignments, where I will post files, and we'll do online exams where we communicate with each other, etc. And YouTube is where I host these video lectures. I will link them to Canvas, but you can also find them directly on the YouTube channel. Okay? But the YouTube is only to store these recorded lectures. This is an in-person course, and I expect you to be here in person. Recording is an added benefit, but sometimes, here, I guarantee you, there's going to be, my batteries would die, or like the audio is messed up, and there's going to be a lecture that's going to be missed. So don't rely that the lectures are going to be recorded every time. It's an added benefit. It's not an expectation that the lectures are recorded. So don't rely on that. Now, if you happen to be ill, for example, and you're staying home, and the lecture wasn't recorded, that's like the worst case scenario. I have like 7 years worth of lectures recorded year after year. I'll point you to the correct lecture and give you the necessary resources so that you stay up to speed with the course, okay? Recorded lectures are posted on my YouTube channel called Professor Saad Explains. Subscribe now, tell your friends to subscribe, your loved ones, the ones you don't love, everyone. Tell them to subscribe to the channel. Kind of helps with the algorithm and kind of with the rankings for the university. So thank you for doing that. We have about, 3,500 subscribers now from all over the world. It's kind of nice to have that outreach for our university and our state and the things we're doing here. Like the videos, if you do like them. If you don't like them, don't say you don't like them. So I'll post the links to the YouTube videos on Canvas. So just give me about a 24-hour lead time to process the video, upload it, and then link it to Canvas. That all takes a little bit of time. Email, I will only email you through Canvas, which is connected to your Umail account somehow. But the only method of communication that I will sanction is Canvas email. Why? Because I care about you. And that means if you send me an email to my work email or my personal email, I am not going to see it. Every morning I come in, I have 1,000 emails in my inbox. And, I don't go through all of them. Sometimes I just select all, delete, because, I know they're probably mostly someone is asking for you to write a paper or review something, and I don't have time for. But on Canvas, there's only 42 of you. And let's say half of you email me. I have 20 messages that I know I need to answer. Okay? So if you send a message through my personal email or work email, I might get to it, but most likely I won't, and I will forget about it. But on Canvas, they're always there. They're not flooded with spam or other email. And the same goes to you, okay? So I'll email you and communicate with you through Canvas. Then you will know that any messages on Canvas are coming from, there's an important instruction coming through the email or an announcement. So make sure your email is connected to your Canvas, or you can access you have alerts about emails and also announcements, okay? Now, student hours, office hours, they're on Wednesdays from 1 to 2:30 p.m. or by appointment. In my office, that's the second floor MEB or the ground floor. MEB is weird. We got like 2 ground floors, but we're on the second level where the computer lab is. Everybody's hanging out there. I'm right across the computer lab. You'll always catch me going back and forth to get water, to say hi to you. There's another way I can sneak out if I want to, run away, but most of the time you'll just catch me there, okay? You're welcome to come in, open door. Even sometimes if I have my door open, just come on in, and chat with me. If you have a question or some concerns any day, it doesn't have to be during those office hours, but I'll dedicate these hours to be specifically for the course. Or if you need an appointment, I can make an appointment over Zoom if you like. These slides will be shared on Canvas, so you don't have to worry about taking pictures of this. All of these slides will be on Canvas for you. But I ask of you, for our time to be effective and productive, to come with a clear question. Clear question. So you can come and say, repeat the lecture for me. You know what I'm going to tell you? I'm going to tell you, go study the lecture, review the video, and what specific items you don't understand. Because most often they're not, when this question comes up, it's the student didn't review, didn't do their job in giving the material a chance. So do your job first, study the material, make an effort to analyze it, because the reality is I cannot learn it for you. Okay, you have to make an effort to learn it. Okay, I'll only try to break down the barriers, explain complex ideas in as simple ways as possible, but it's up to you to learn the thing, right? I already know it, and only you will know where the gaps are. Okay, so make an effort and come with clear, specific questions, and we'll work through them. Even if there's gaps, I'm happy to go over those gaps, like from calculus or vector analysis or whatever. I'm happy to help you with those as well. Okay? We will have 4 help sessions in the ICC or the Dougal lab. That's the computer lab on the 2nd floor, to help you with homework and exam preparation. On Tuesdays, Lillian will run the help session every Tuesday from 1 to 2. And then 4 to 5, Davin will run the session. Same thing on a Thursday, but we swap. Davin runs the 1 to 2 session, and Lillian runs the 4 to 5 session. Over the years, I reckon these are the best times to run these help sessions. We get the most students in those help sessions. I know sometimes your schedule will not work with those, so then I'll have to rely on you to tell me that I need help with this or help with that, and then we can figure out ways to schedule something and sit with you to help you, okay? Technical help and support. Everything goes through Canvas email, but not only that. You're gonna email me and Davin and Lillian. Each and every email related to the course, okay? Why? Because between the 3 of us, we're more likely to answer you in a short period of time versus you just emailing Devin, for example, or just me, right? Between the 3 of us, we have a rotation that we go over Canvas email every day, and you're more likely to get a quick answer if you email the 3 of us, okay? So make sure you put reply all and email all of us. And sometimes if you say email one of us, we will respond to you and copy the others so that everybody is in the loop and we understand what's going on in the course. If it is a personal issue or something you just want to discuss personally, you come to me, not to Davin, not to Lillian. You don't copy them. You just email me directly, and I'll figure out a way to help you, okay? No textbook. My class notes are based on this book by Chopra and Canali called Numerical Methods for Engineers. I have some of the chapters uploaded. That's the things that we'll cover. So you don't have to buy anything. You can just use those PDFs. But my class notes are more than enough for you to learn everything that you need to learn. All right, homework assignments. We will have up to 10 assignments this year. Up to 10, maybe 9 or 10. I think we'll hit 10. 2 of the lowest assignments will be dropped, and therefore there are no homework extensions. Okay? So, you couldn't make it for that homework assignment. Well, it's not going to count. Okay? So no homework extensions. Okay? Assignments will be posted on Canvas, and you are expected to upload your submission, which is the answer to the homework assignment, as a Jupyter notebook. Does anybody know what that is? Okay, does anybody not know what a Jupyter notebook is? Okay, so we'll have to fill in that gap. We'll talk about this a little bit later. But Jupyter notebooks are essentially a way to combine, to just do your reports, including code and math and text and results and plots in one file, in one thing together. Okay? In the past, people would do MATLAB code or C++ code, and then they run the results, they have plots, and they got to create a Microsoft Word document and install math type and write the math, put the plots. You have like 50 files just to make one report. A Jupyter notebook does all of that for you in one file. You write your code, you get your results, you discuss your results, you make your plots there, everything is in one place. So that will be the format that you work through your homework assignments. But you will upload that file, and you will also upload a PDF version of it. Why? Because we are only going to grade the PDF version. And the PDF version has to be the latest and greatest of your report. So if you've done Jupyter Notebooks before, you know there's code to run, there's results, etc. You run all this, make sure all is good. You convert it to a PDF. You upload the notebook and the PDF. We will grade the PDF. Okay. Homework is generally assigned on Thursday and due the following Thursday. If you're a little late, there's a 25% daily penalty for late submission. So up to 3 days, you lose 75%, and then fourth day, it's not worth it anymore. Those with formal CDA forms are provided extensions as needed, but no more than 3 days. I don't provide solutions, but I discuss solutions in class, work together, because there's 1,000 ways to program, an error analysis or a Taylor series, right? So I'm not going to give you prescribed one way of programming or the other. Instead, we'll discuss the solution in class together to demonstrate to you how, we think about things. Assignments will receive some partial credit, as we'll discuss in a little bit. Your submitted Jupyter Notebook has to just run. So suppose, we look at your PDF and we're like, okay, we don't know what's going on in your PDF solution. Remember, that's going to be your formal report. So put yourself in a position where you are working for a client and you submit your report to the client. You got to give them you check your report before you submit it, right? Imagine you're submitting an application for a scholarship. You check your document before you submit it. So make sure you check your document before you upload them to Canvas. Let's say for some reason something happens to the file, it doesn't get submitted cleanly, and then we have to look at the Jupyter Notebook. So we open the Jupyter Notebook, we're just going to run it. If it doesn't run, as far as we know, it's not working. Okay? So make sure before you submit, make sure your Jupyter Notebook all runs cleanly and works so that we at least can give you credit when a PDF is missing. Okay? We will not debug your code. We're not this is not a course about coding. Coding is essential and fundamental, but this is a course about solving engineering problems with numerical methods. So we'll help you. I'll discuss this more in a minute, but we will help you with your coding. We'll help make your coding better. But again, I'm not asking for fancy code, just code that works, that can solve the problem. All right, but we're not going to debug your code in your homework assignments. And if you TA for me next year, you're going to realize why we don't debug code, because there's probably for every homework assignment, there's going to be over 200 lines of code times 42 students. That's an impossible task to do. And then times 10 homework assignments. So we don't debug your code. We'll help you in the help sessions, fix your code and debug it as you're working on your homework. Feel free to email us every hour, hey, can you help me with this code? I don't understand what's going on. We will be happy to help you with that, okay? We'll help you debug it there, but once you submit, we're not going to fix your coding errors. We just can't. We don't have the resources to do that. And it's your responsibility to make sure that the notebooks are complete and can be executed without error, okay? So a little more on homework assignments. They must look and read like a regular report, except that they will have code included with them. And therefore, you must include discussion of your results. So for example, let's say, so this is a for loop that calculates the sum of 1, 2, 3, 4, and 5. Okay, you might, run this code and then print the result and prints 15. That is not an answer. We will not read this, so assume we don't see this. What I'm expecting of you is you do this, you print it, but then you write something to me. You say, as shown above, the solution is 15. This is because this and this and that. So take the result that you've printed out, even as fancy as your print or your output is. That is not considered a report. A report needs to take those results and put them in context. The only exception is a plot, because you can't take that plot and write it. So if you had this print and then you had a plot, the plot, you keep it the same and you refer to it, but that number or any results that come from your programming, any output, you need to discuss it and put it in context. Because if I'm looking at this 15, what is 15? What the heck is 15, right? But when I read this, that's a human person who wrote to me something, put 15 in context, okay? Formatting should be clean and clear. You have freedom in formatting it. Okay, I am not going to prescribe formatting for you, but it needs to be, decent. You're going to be engineers. You're going to reflect on our department and our program, right? You need to have a decent reporting. You need to put the effort to make your report readable and understandable. If no discussion is included and we cannot interpret the result, then we cannot give you any points, because I don't know how to interpret your results. I'm not going to interpret them for you, because I will always interpret them the wrong way, okay? So, you have to put the interpretation. These are your results. If we can interpret the results, but no discussion is provided, you lose 50% for that question. Okay, so this is all described in the syllabus. Here's an example of a Jupyter Notebook report. I have this template on Canvas in the files directory, and it's linked in the front page. So, for example, homework 1, CHEN 2450, your name, your unit, and if you want a little description, then problem 1, question 1, solution, question 2, solution. Right? This is clean. This is clear. This is what you would expect of me, right? Imagine I just give you code. You're like, what the heck, professor, is this, right? So if you expect this from me, I at least expect something close to that from you, okay? You do this now, this year, it will be easier next year. Because in your junior year is what we call your cognitive enlightenment. You're going to be barraged with topics that are so intertwined and complicated, you don't have time to worry about writing stuff like this. So get this out of the way this year so you're faster at writing your reports. Like I mentioned earlier, we don't give full credit for homework, only some partial credit. We don't give partial credit for homework. We give some partial credit. And why? It's because I give partial credit on exams, because exams are a different situation. You have a limited time to finish the exam. You're kind of stressed out. You got a bunch of things going on, right? We'll give you a lot of partial credit there if it's of the handwritten type exam. But for homework, you have a week. And I want you to start getting trained to getting things right. Because there's no room for error as an engineer. You don't want to go on a bridge there's a risk it's going to collapse because the engineers who designed it were like, yeah, you know what, we got that a little bit right. No, you got to get it right. You got to put your best effort to get it right. So there's little partial credit on homework assignments. So if the method is correct and no errors, you get 100% credit. If the method is correct but contains some arithmetic or minor programming errors, you lose 20% per error. That's harsh. And it's intended to be harsh because you need to get it right. You have a week to work through the homework assignments. You start early, you work through them, you make sure you get all your calculations right. And oftentimes, the answer will not make sense if it's wrong. So you go back and revisit your calculation, you get them right. And you know what? It works every year. So for example, let's say you had a typo in one of the factors in your formula, or you looped over n plus 1 instead of n. That's a minor arithmetic error. You lose 20% per error. It is your responsibility to make sure your code executes. So I cannot keep we will not debug your code, but sometimes we can spot a quick bug, right? And we'll give you a credit when we can. If the solution contains a minor theoretical error, so those are more grave errors. The theoretical errors means there's a problem in the understanding of the material. So for example, in calculating the sample-based standard deviation, use n instead of n minus 1 in the denominator. This is a theoretical error, not a programming error, okay? Because you typed in the formula, right? You put n instead of n minus 1. That's an understanding error. If no discussion is included and we cannot interpret the results, no points will be given. If we can interpret the results but no discussion, like I said, is provided, you lose 50%. All other errors, you'll get no credit for the question. Now, that doesn't spill over to the next question. Okay, so if you got that one wrong, the next one we're going to assume that, most of the time they're separated, the questions. Okay, they're separate, so they're not connected to each other. So result for question B is not going to be dependent on question A. So you're good there. No quizzes this year. Yay. Okay, I'll put a smile on people. Okay. No cell phones this year. So this is new this year. Make sure that you got your phones. shut off, stowed away. It's very distracting to you, to me especially, as I'm looking at you and trying to engage with you and have this direct line of communication, looking you in the eye, listening to you, reading your body language and all of that. If you're on your phone, it's distracting to me. It trips me off. It's distracting to others, distracting to you. If there's an urgent discussion, feel free to step out, be as loud as you want outside, and come back in and be focused with me, okay? So please avoid that. I know you're on your laptops. You could be on social media or whatever on your laptops. You're only hurting yourself doing that. It's only an hour, 20 minutes here, of very precious time for you and for me as well. So, you can postpone those discussions for later. If you're feeling unwell and you have and I know now it's going to be season for flu and whatever things are flying in the air. If you're feeling ill, you have fever, something, just stay at home. Let me know. I'll make sure you get the right material for you. Go get rested, sleep it off, drink water, and whatever you need, and we'll make sure that you get the right material. If you need to work up so here's what you do: you stay home, you notify me, you keep up with the class. I'll make sure that you get all the necessary information. If you need some certain accommodation, let's say there's a deadline, this illness really knocked you off, and you're gonna late on homework, etc. We can discuss accommodations based on the illness, but I will ask for a doctor's note in that case if you're requiring accommodations, okay? Just to make sure that the illness is, because I don't want everyone to just abuse this policy, because there's no homework extensions except in these kind of extenuating circumstances, right? Also, this applies if there's some tragedy or event, life happens, in family, etc. Unplanned things, come and talk to me and we'll work something out, okay? We will have 3 exams and a final. Study guide, I'll give you study guides and sample exams as best I can. And really the study guides are going to be based on your question. What we will do after we finish every chapter or every unit, I'll have a Q&A session. So I'll open up a submission for you where you submit questions and we'll come and answer them together. So you'll have a list of Q&A, 60, 70 questions and answers per topic. So that's going to be your best study guide. Exams might be of the handwritten type or entirely online. Usually I blend both. A couple of exams will be entirely online on Canvas, and a couple of exams will be handwritten, okay? Handwritten type exams have less questions than online exams, but they're longer because they have more derivations, so maybe 2 questions or 3 questions with derivations. Online exams, they have 30 questions, but they're usually low stakes questions, just general comprehension, multiple choice, or essay questions. Adequate partial credit will be given only on handwritten exams, but no partial credit on online exams because you'll have 2 attempts to do it. Online questions in online exams will be randomized. So the second attempt, you might get completely different set of questions in the same spirit, okay? So typically, most students just do 1 attempt and they're fine. Exam 0 is next Thursday. Whoa. Well, it's going to be for your prerequisites, right? So I want to make sure that you know the material that you need to know to get this class moving. It will count for 5% of your grade tentatively. It's only 15 to 20 minutes long, covers prerequisites, and I'll send you a study guide and information about that. So essentially, how to add 2 vectors, how to multiply 2 vectors, do a basic derivative, a basic integral, in a little matrix, rows and columns. So I'll give you the material for that, the study guide. Everything related to exams will be posted in announcements and posted on the front page in Canvas. Canvas is your go-to spot to get the latest information. That front page is critical. It gets updated every day, okay? Exams 1 and 2 are the 2 midterm exams. They're 17.5%, again, tentatively each. They cover only recent material. So in part 1 of the course, after part 1, we'll have an exam that covers only part 1. Part 2, we'll have an exam that covers part 2. But there's elements of part 1 that are going to spill over to part 2, because in part 2, we're going to be bound to have some linear systems of equations. We studied those in part 1, so, but they're going to be lightweight in part 2. So they're not directly, the questions will not be directly on items from part 1, but some elements from part 1 are going to spill over to part 2. And final exam is going to be comprehensive with heavy emphasis on the last part of the course. All exams are closed books, closed notes, closed laptops, closed everything, except you'll have a note sheet with you that you write, you prepare at home. You can typeset it. You can write it yourself. Exams 1, 0, 1, and 2, it will be one sheet double-sided. For the final exam, you'll have 2 sheets, okay? Double-sided as well. Okay. Partial credit policy for exams, like I said, for handwritten exams, you'll get a lot of partial credit because your handwriting, you're kind of stumbling on mistakes. There's derivations. There's a lot of algebra going on. You get a lot of partial credit. Online exams, no partial credit because they're like easy questions. One second. Easy questions, low stakes question, like what is the standard deviation, or explain this numerical differentiation. One answer right, you either get it right or wrong. There's no partial credit there. Yes?
Are the online exams at home?
No, we'll do them in class. Yep. Okay, tentative grading policies looks like this. Assignments are about 35%. One prerequisite exam, that's exam 0 next week, 5%. Two midterm exams, 35%. And the final is 25%. And this is the grade distribution. What you're getting for your letter grade and the numerical grade. Okay, this is, again, these will be shared with you. Last year, I started doing a visual syllabus, which is also posted on the main page and in these slides. So I know syllabi are like long. They're like if you've ever, there's this one professor who printed the iTunes user agreement, and it was like 100 meters long or something. Yes.
So with the online exams, are you going to take the online exam and then do the written exam, or are they just taking that?
No, either the exam will either be an online exam or a handwritten exam. So let's say exam 1 and exam 0 will be online next week. That's it, right? Exam 1 might be online or handwritten, not both. Okay. Yeah, that'd be really bad. Yeah.
Also, the note sheet, is it like a standard?
Yep, standard letter size, double-sided. Yeah.
Just a whole piece of paper?
Yep, whole piece of paper. Yep, if you don't mind. Yep, this would be like a letter size, double-sided. You can write on both sides. Some students have used a font size of 5. They bring a magnifier to read what, I leave that up to you. Okay, but I also provide you with a formulary, on the exams. And so, anyway, I'll give you most of the formulas. On those note sheets, what I will recommend eventually is that you just kind of fill in methodology of thinking, like how to do, what steps do I need to do to solve this kind of type of problem. Now, this visual syllabus is so I was saying about the iTunes user agreement. So, you look at the syllabi, like these days, they're like 17 pages long. I know nobody reads that. Last year, I put a $50 reward. I hid it in the syllabus in a statement, and I said, it's placed in a box with one of our assistants, and nobody came and claimed that $50, so I took it out after the first week. So nobody is going to read the syllabus, okay? But I will still ask you to read the syllabus. But this is a summary of what to expect in this course, summary visual syllabus. So use that. And we'll talk about AI policy. Oh, speaking of AI, we have a new thing this year. What do you think this is? This is DALL-E, generated art. Okay, you know what DALL-E is? It's, that ChatGPT. Yeah, everybody knows, right? Yeah. Okay. Okay, so I'm going to introduce you to Cadmus and Cadmus TA, which is going to be your AI teaching assistant. Okay, this is entirely experimental, and I've been training this AI chatbot for the summer. I started it last year, but we couldn't make it free last year. You needed a subscription with ChatGPT. This year, it's going to be free. So if you have your laptop in front of you, I want you to go ahead and point to one of these links, cadmus.tsad.net or cadmus.tonysad.net. And you just have to log into ChatGPT. If you have an account there, log in with that account. If you don't have an account, you can sign in with Google or anything. There's Google, there's Facebook logins. Cadmus.tsad.net. Okay, so log in. Okay, I'm gonna open up my browser. Can continue with Google or whatever you have an account. cadmus.tsaad.net. Oh, it might give you a not found, just refresh it. All right. So, okay. So it will take you to our only AI-sanctioned TA for this course. This is purely experimental, okay? But I'm going to rely on your feedback to make a big change in the college. So you are the first class, as far as I know, in the College of Engineering, or at the U, actually, who is experimenting with something like this. So I'm really proud to be leading this effort and for you to be part of it. Okay, so I want you to use it. Now, this is trained and will continue to be trained on my material, okay? So, and it's going to be biased. The way I'm training it, I'm biasing it to give you answers from my material. It's still connected to the rest of GPT, so it might give you outside answers. So that being said, take the answers with a grain of salt. Most importantly, don't come and tell me, your TA told me this is the answer. No, I'm going to tell you, no, you can't hide behind that. Because although this is part of what we're doing, it's experimental. It's kind of trying to, I know you're going to be using GPT, so you might as well use something that is trained on some of my data, okay? So the best use for this is definitely to figure out and help you sort out things from the syllabus. So for example, what is the homework policy, right? Assignments, up to 10 homework assignments, et cetera, late submissions, right? Summarizes things for you. Okay, so it gives you most of the stuff that's in the syllabus. Okay, so let's say when is exam 2? Exam 2, oh, however, the specific date, well, no, that's wrong, okay? It is in the syllabus. Syllabus, what date is exam 2? Right, so it's still a little silly sometimes, but then it searches, there you go, Thursday, October 31st. All right, so bear with it. It's still kind of training. I'm still uploading data and material to it. Okay, limit of using GPTs. Oh, try again, and of course, it's gonna require a Plus subscription. I didn't know that, I'm sorry. Okay, does anyone have a Plus subscription? Yeah, okay, so it's gonna limit it to 11, try again in 11 minutes because I was trying this earlier at home. So let me get my subscription and kind of show you a little bit what it can do for you. Are you still able to try it? Yeah, okay. Yeah, great. Yep. So I think it will let you try. I don't know what the limit is, but with the free account, keep trying. Okay, so I'm going to show you some the more fancy stuff you can do with it. It's really cool. Okay. So summarize the exams and dates. Let's say dates for me in a table. Don't you love it? Well, again, date not specified. Hey, silly, you know. The dates are specified in the syllabus. So, you know, be tough with it, okay? The syllabus, please check again. All right, now it's searching its knowledge. Okay, let's see. Second week, there you go. Okay, now I got it right. Okay, so the previous date was wrong. So make sure you check your answers, right? Make sure you check your answers. But I want you to experiment with it. And let me know at the end of the semester, I'm going to do a survey and see if it made your life easier or made it a living hell. Like every answer you have to go check in the syllabus, etc. Now, there are some notes already uploaded on error analysis, etc. And so you're going to start interacting with it on technical stuff. So for example, I'm going to ask it, what types of errors are discussed in this course? True error, approximate error, relative error. Okay, that's all correct so far. Okay, iterate, truncation, round off, etc. You can tell it, summarize the errors for me, right? Put them in a table as you prepare for exam analysis, exam study, right? But make sure that's consistent with what's in the slides, please. Okay, so I'm only doing this as an experiment, but do I stand behind it? Probably not, because it's still going to make mistakes. Nobody's standing behind these AIs, because even the chatbot tells you, please verify your results, because I don't know what it's going to make up. It might make up something. Okay, it will help you with programming for sure, like how you can improve your plotting, etc. And all of that, just use it, run it through this, or the standard GPT, but why not just run it through this, okay? Now, if you want something very specific, make sure you tell it, what does Professor Saad say about this? So, for example, what does Professor Saad say about best programming practices, let's say? Okay, Python as the preferred language, okay. Clarity in code, critical thinking over coding, testing and validation, okay, sure. What is the best debugging strategy according to Professor Saad? Okay. So you will notice as we go through the course, there's a mantra that numerical method students come out with, and it says, when in doubt, print it out. Okay, and it picked this up just from my transcripts from my previous YouTube lectures. Okay, so it can parse knowledge correctly and try to connect it, but to force it to give you the answer that I would have given, make sure to say, hey, what does Professor Saad say, or in this course, what are we told about something or a topic, okay? And you can ask it, tell me more about Cadmus and his origins. So Cadmus is the first teacher from Phoenicia who gave the alphabet to the Greeks. Okay, so historically he was the first figure. They call him the first teacher. He was also a warrior. So but I'll take the first teacher. That's why I called it Cadmus. Okay, as being a teacher that's going to assist you with this stuff. Okay. Yep. So he was the son of Agenor, the king of Tyre, a city in Phoenicia, and Telephassa, etc. Anyway, so stuff like that. All right. Okay. Good. Fun stuff. Your TA assistant. Again, it's experimental, but feel free to use it and let me know how it's going. Right. I'm going to keep training it as we go through the course. I'll be uploading like the Q&As and all the lecture transcripts will be uploaded, so it has a ton of knowledge, all right? But again, take it with a grain of salt, please. Okay, let's come back to our slides. Let's see. Okay. Cadmus TA, let's see if we can go through. All right. Now, a little perspective on, I don't have much time, so I'll try to go through this a little faster. A little perspective on where this course kind of sits by is that in all of engineering and physics and stuff you're going to be learning, you have these fundamental conservation laws that rule everything. So, Newton's law, conservation of momentum, conservation of mass, conservation of energy. Those are the foundations of everything we do in engineering. All the equations we derive are based on our faith that the universe is going to conserve mass, going to conserve energy, going to conserve momentum, and all of those things. So those are the fundamental laws that we engineers, physicists use to kind of develop our equations, right? There are also approximations and models to these conservation laws, and we come up with what we call an algorithm, which is a set of steps to obtain an answer, okay? Now, once you have an algorithm, so an algorithm would say, okay, write the equations, convert the derivatives, or convert these nonlinear equations, linearize them. Okay, these are the algorithmic steps, but then you have to go and implement those and convert them to numbers. So you could always, or sometimes solve by hand. That's pencil and paper and calculator to get a solution, very limited in scope. Or you could actually use numerical tools for more sophisticated problems to help generate plots, calculate numbers, etc. Okay, so these are the other courses in chemical engineering up there. This is 1703, where just some numerical tools using Python and Excel. Okay, you use that. Numerical methods is this one. We are here. So in a way, you started here. Now you're moving up here. Next year, you're going to go up into conservation laws, where you're going to study heat transfer, fluid mechanics, mass transfer, thermodynamics. Okay. My teaching philosophy. If you take an average classroom and plot the attention versus lecture, versus time through the lecture, initially everybody's suspicious of the professor. Then they get engaged and excited, about 15 minutes into 10, 15 minutes into the lecture, and then everybody falls asleep. Okay? And then by the end, oh yeah, we're gonna go home. Everybody wakes up, and then we leave. Okay? So that's horrible. I'm like that. Like within 10 minutes, if the lecturer cannot keep me engaged, I'm gone. Okay? My time is precious. I'm here to learn something. If they cannot keep me engaged, I'm gonna leave. Okay? So this is normal. This happens typically, but 10, 15 minutes is what the research shows. What if we can do something like this, right? And to accomplish this, there's this, approach where every now and then you introduce an activity, you tell a story every 5 minutes, you take a break, you do another activity, give the students a break, stretch their legs, get them, awake. So every 15, 20 minutes, you try to reset the class as if you're going back to the beginning. And that's the approach I like to take. Okay, now we didn't do that today because, there's just so much to cover, right? But there's another way to do this is you'll see that I use a lot of storytelling techniques, and you'll observe that throughout the course. There's always a story in almost every lecture. I move around, I gesture, I'm loud sometimes, and sometimes I'm quiet, right? Just to try to keep you as engaged as possible. My approach in general is inductive based. So there's two general ways to teach things. There's deductive and inductive. Deductive is you start with the law. Here's Newton's law, F equal ma, solve all of these problems. Okay, that's deductive. Inductive is like, I drop a ball, it falls. I drop a feather, it falls, but it kind of moves slowly. I drop a cannonball, it falls. And then there's, let's plot the falling rate versus the mass, etc. You discover the law inductively, okay? So I'm generally an inductivist. I teach by induction because that's how we learn about the natural world, right? But that also does not exclude deductive thinking, where you already know Newton's laws, for example, right? So if we have a problem where we're looking at the parachutist falling in the air, we're going to study the air resistance and whatever, I'm going to assume you know Newton's law, right? F equal ma, and you can just apply it to that problem. So there's some deductive components, right? But most of the stuff, because especially this course is a second-year course, right? We're going to go through induction. We're going to make problems, look at things, and ask what's going on, and try to discover the law or the rule together. And I think that's a very effective way. I also use an active-based learning approach. I'll explain this more on Thursday. You'll form into groups, and you'll have a name tag for your group. And instead of working individually with you, I'll work with your group, okay? to shelter the individuals a little bit. But, we will be calling upon groups, so I'll ask you to do that on Thursday, okay? This class is not about numerical, this class is about numerical methods, sorry, not about programming. So the goal of this class is to teach you about techniques to implement methods to solve complex equations on a computer. It's not about programming. This is not a programming course. If it were, I wish it were a programming course, but I would have to make it 17 credits or something, right? Which nobody will agree on, right? So, we'll get some programming along the way. That's why I ask you to brush up on your programming. We expect you to know some programming, and you will learn that by the end of the semester, there's only 5 or 7 things you need to know to get through the course: Matplotlib, NumPy, and quadrature, a couple of things, and that's it. A for loop and a while loop, and you'll be able to do almost everything we're going to do in this course, okay? Now, to do serious numerical methods, you need programming. So that kind of makes somewhat of a paradox, right? So that's why you need to brush up on your programming skills now. We use programming extensively. We will work together on improving your programming, but you have to make a serious effort to learn. If you have absolutely no programming background, that's going to be hard, okay? Because again, we're not going to be introducing or teaching programming. And the problem is when you teach programming for the sake of programming, nobody learns anything. So the benefit of this course is that if you have some programming inclination, you've done some programming, you come and put this programming in context of realistic problems that we're solving, then those make sense. Then you'll understand why you're writing a function, why you're calling a for loop to solve the actual problem, okay? Start on homework early. It's not high school. You're going to be so overwhelmed. I assign the homework, start on it immediately, even just reading it, so that your brain starts thinking about it, okay? Review class notes prior to the lecture. Most of the time, I put the lecture notes at the beginning of before I start the lecture. I have to update them oftentimes with new material, so I'll keep them updated online, but you can get access to the lecture material before the lecture starts. And review them after class if you can. Before doing homework, try to rework the examples we did in class. And if you're stuck, just get help. There's no way for me to tell that you're stuck. Right? I promise I don't have trackers on you. I don't know what you're thinking, what's going on in your mind and in your world. You have to come and tell me. If you feel like you don't want to come, just come talk to Devin, come talk to Lillian, all right? And then we'll work something out. But if you're stuck, you got to seek help, okay? Take advantage of discussion and help sessions. For homework, getting the answer is not the goal. What I care more about is for you to be able to assess whether your answer makes sense or not. Okay, that's very important, especially in exams. Like, you could get the wrong answer, but tell me this answer doesn't make sense because of this and this and that. So one time I told my students, if you tell me that, then I'll give you full credit. So everybody wrote on the exam, like, this answer doesn't make sense, but why doesn't it make sense? So you got to tell me if your answer doesn't make sense and you're running out of time, tell me this answer doesn't make sense because the temperature in the middle of these two objects cannot be higher than any one of those two objects. That's just common sense, right? I'll give you full credit for that, okay? So keep that in mind, that the answer is not the goal, but the critical thinking about the answer is the goal. Writing code is not the goal. I care less about you writing Shakespearean level code. I don't care, okay? I'm not going to read your code. I'm not going to judge you on it, okay? I will make suggestions like this is better than that, etc. But writing code is not the goal. The goal is to solve the problem, okay? And how you present the results is often as important as the results themselves. Okay, so I have 1 more minute before I let you go, but I'll give you some thought about programming. And on Thursday, I'll pick up from here and continue to discuss with you why Python and why coding is very important, and that is going to become obsolete in 10 years. So many people, many students fret about MATLAB, Python, C++, etc., Java. I don't care. This is only programming language. What matters are the ideas behind the programming. I'll give you an example. I speak like 6, 7 languages, okay? I can express the same idea in all of those languages. The language is only clothing to the idea. Okay? So whether you use Python, MATLAB, C++, it doesn't matter. That's syntax, that's clothing that you can get from ChatGPT or Google. How do I write a for loop in MATLAB? How do I write a for loop in Python? What matters more is knowing that you need a for loop. Okay? Knowing that you need to sort an array to solve this problem. So I give you a bunch of data, and it's all scattered. And I tell you to do interpolation. You need to know when you're doing interpolation, you will learn that you need to sort the data first before you do the interpolation. So knowing that is more important than how to accomplish it in Python, because accomplishing it in Python is documented. You go on Google, you go ask your friend, right, how do I sort an array in Python or MATLAB? But what matters is the idea. If you know the concepts that you need to do at this step, you can Google it, you can find the answer and implement it. All right? Pleasure having you this year. I'll see you on Thursday, okay? Have a great semester.